vignettes from the last class, reminders of what we did, because most of that told stories in the last class. But that's better than going through the welding stuff anyway, because you might be able to use the stories someday for humor or something. But we did talk about different types of boundary layers, so far as that goes, and it's typically the thermal boundary layer is going to be on the order of several tenths of a millimeter, but the distances over which the electrons collide with each other is on the order of 10 to the minus 3 millimeters. And if you think about that, it works out to about 10,000 collisions before the electrons thermally ionize, or thermally come into thermal equilibrium with the neutrals and the ions, which are so much heavier. And the device screening length is something else. Basically, is how far away can you see the electric charge? And that's like 10 to the minus 5 millimeters. So when you read the literature in welding, they'll often talk about these things being very short distances. They usually talk about the device screening length. But the thing that's important for us is really the thermal boundary layer. We also talked about the fact that plasmas or welding plasmas are partially ionized plasmas, where I have 5 to 30% ionized. This is the line for argon ions as a function of temperature, and this is the line for argon neutrals. And if I'm 5 to 30% ionized, that's going to be somewhere in this region, which is around 11 to 12,000 degrees. And if you measure the temperature of an arc, that's what you get. So everything's self-consistent so far as that goes. Those are some of the things that we actually did cover other than stories. But now let's talk about different types, get into something a little more practical, different types of shielding gas. And actually, I guess I can hide from you the rest of this, or work through it this way. So if I have argon, and where do we get our argon in the world? Anybody know? Air is composed of 78% nitrogen. How much oxygen?
21.
Around 20, 21. What's the other 1%?
Argon.
Oh, it's argon. Okay. Air is about 1% argon. There's lots of argon in the world. And in fact, they liquefy air and then distill it, and you end up with liquid nitrogen, which we use for freezing vegetables, a lot of your flash frozen vegetables and things. But it's a cryogenic gas, and it's fairly cheap. Like, I don't know what it is now with energy costs going up, but it used to be like 15 cents a liter for liquid nitrogen. Pretty cheap. And liquid argon, on the other hand, might be a couple of dollars a liter, but argon's fairly cheap, okay, because it's 1%. It's sort of a byproduct, because we use liquid oxygen. It's very useful. Virtually all the steel in the world, 800 billion tons or a trillion tons a year or something like that, or a billion tons a year, is basically made with pure oxygen. And so we get that, so you have a lot of liquid nitrogen and liquid argon left over. Argon is valuable because it's one of the ways you make stainless steel. As far as that goes, in fact, the process was invented right in the basement of Building 8 over here back in the 1950s. Revolutionized the stainless steel industry. But anyway, we've said that 80 to 90% of the heat is carried by the electrons in this gas boundary layer, going across this gas boundary layer. So if I've got, this is my arc, this is my surface, I've got a gas boundary layer, and the electrons punch through and carry with them the heat, the Thomson energy, the energy achieved by being accelerated across the anode fall space, and then decaying down to Fermi energy. But you also have the hot gases, and so you've got a boundary layer, which most of you studied boundary layers, right? Anybody not studied boundary layers before? Okay, I figured, some of you might not have, but don't worry about it. You'll study them eventually around here. Anyway, in the boundary layer, we kind of draw the velocity diagram. As you have some free stream velocity, and then it decays down to 0 down here. That's why we call it the boundary layer. And the thermal boundary layer temperature profile is going to look similar. Okay? Well, actually, it is going to look similar. And so the heat flows from the hot gas down through this boundary layer, and that's controlled by the thermal conductivity of the gas. Okay? Now, whether it's 80% or 90% of the electron heat, depends on the current, whether you're a 100 amp arc or a 200 amp arc and stuff, but let's just take 80% carried by the electrons. And that means the gas boundary layer, the hot flame, if you will, is carrying about 20% of the heat. Okay, so 2,000 watts per square centimeter. If I have 10,000 watts per square centimeter, 2,000 is coming from convection and conduction across the boundary layer, and the other 80% is coming from the electrons. Now, if I switch gases, one of the gases that we can use in this country is helium. Where do we get helium? Texas and Louisiana. It turns out the natural gas in Texas and Louisiana has a very, very small percentage, like 1/100% or something, of helium in it. The air has a very, very small fraction, like 0.0005 or 0.002% helium. So you can get helium by liquefying air, but you got to liquefy a lot of air. And in fact, the Europeans, everyone else in the world, gets helium either by buying it from the United States, because we have these reserves of natural gas in Louisiana and Texas that have a very high concentration of helium, and don't ask me geologically why, I don't know. Or they get it by liquefying air. So when I was a student working on superconductivity, we were paying $2 a liter for liquid helium because it was, the government had a price support. Because originally people were just burning the natural gas and the helium was going up their home stacks, okay? Because they weren't separating it out. So back in the 40s or 50s or whatever, the government told the gas producers that we will buy all the helium that you produce out of natural gas rather than wasting this resource, which is the only resource in the world other than distilling it from the air, liquefying the air and distilling it. At that time, it was the price of helium in Europe was like $10 to $20 a liter. It was like 5 to 10 times as much. And then in the late 1970s or 80s, the government said, nope, we're not going to pay for the helium anymore. We got to save our budget. And so they basically, we just burned the helium out. Okay. Although to a certain extent, the gas companies will still extract some of it, but they don't extract all of it. But basically, we have about a 30 or 50-year supply of helium until the natural gas in Louisiana and Texas runs out, and then we will be paying 5 to 10 times as much by liquefying. We don't destroy the helium in the world. It's still there. We blow it off into the air, but we're just increasing the entropy and the cost to get it back out. Okay, so that's where the helium comes from. But because helium is relatively cheap in this country, at least for the next 30 to 50 years, we can use it for welding in this country. It's very rarely used in other places. Okay? But if 80% of heat is going to come from the electrons, helium has a much higher thermal conductivity, and in fact, the thermal conductivity of the gas goes as the inverse of the mass of the atomic mass of the gas, inverse square root, if you go through the kinetic theory of gases. So if I wanted to compare argon to helium, argon has an atomic weight of 40, helium has an atomic weight of 4. The square root of 10 is equal to 3. You know that, you're in the math department now, right? And so there's about 3 times the thermal conductivity of helium across this gas boundary layer as there is of argon. So if in an argon plasma, 20% of the heat is going across as from the conduction, the thermal conductivity of the gas, then in helium I'm going to get 3 times as much. So if my total normalized heat for argon is 1 or 100%, helium is going to give me 40% more heat transfer because of the thermal conductivity across the gas boundary layer. Now this is a total variance with the Welding Handbook. The Welding Handbook will tell you that argon has an ionization potential of 15, and helium has an ionization potential of 24 volts, and therefore helium has, there's more, takes more energy to ionize the helium, and therefore it gives you a hotter arc. The problem with that is if you make mixtures of argon and helium, you don't find that that's true. You don't have a hotter arc in terms of degrees Kelvin. And in fact, it turns out that when you're welding on a liquid weld pool, the thing that controls the temperature of the arc is not the argon or the helium. And I told you before, if you had a pure argon arc, you'd get 11 or 12,000 degrees. Well, it turns out if you're running a pure argon arc on water-cooled copper, that's true. But if I actually were to measure the temperature by measuring the spectral intensity over a liquid steel weld pool, I might find the temperature is anywhere from 6 to 7 or 8,000 degrees Kelvin rather than 10, 11, or 15, because the metal that vaporizes out of there is much more easily ionized, and I only need like 5% or 10% or 15% vapor to produce the electrons. And remember, I told you that I don't care about voltage. You mentioned voltage. It's current that carries the heat. And voltage, the arc will develop whatever voltage is necessary to ionize the gas. And if I have easily ionized metal vapors in that arc, I will have a much lower temperature. The arc will go down to its lowest possible temperature to generate enough electrons to carry the current that the power supply is imposing on it. So it turns out the heat transfer is not controlled by the ionization properties of argon and helium. It's controlled by the ionization properties of the liquid metal you're melting, which could be aluminum or steel, and they're all about the same in terms of ionization potential, 5 or 6 volts instead of 15 or 24. But the welding handbook still tells you this. And in fact, I grade the certified welding engineer exam, and they usually have that question on the exam, and I have to grade it as if it came out of the welding handbook wrong. I mean, I grade correct. If the student says what the answer is in the welding handbook, I give full marks, even though scientifically that's wrong. Okay. But anyway, so helium does give you more heat transfer, and so there are times you're welding a pipe with gas tungsten arc welding, you're having problems getting penetration. What can you do? You can use helium. Okay, or argon-helium mixtures, typically, because you're still trying to save money. Helium costs a lot more. Now, another thing you can do is you can add hydrogen. You can't do this when you're welding carbon steel, but if you're welding stainless steel, you can actually add hydrogen. In Europe, they actually do use argon-hydrogen mixtures quite often for stainless steel. We tend to use argon-helium because we have cheap helium. But if you still get 80%, the electrons are still carrying their fraction of the heat. It turns out hydrogen, not because, well, actually hydrogen has two things that happen. Hydrogen is even lighter than helium, so it's the square root of, compared to argon, 40 over 2 plus H2, right? And so that's square root of 20, which is 4.5 or something like that. So hydrogen carries more heat, but hydrogen does one other thing. Hydrogen carries the heat of recombination. Up in the middle of this plasma, I'm dissociating hydrogen into monatomic hydrogen. It takes energy to do that, to break apart the hydrogen diatomic molecule. When it gets down in this cool boundary, relatively cool boundary layer at 3,000 degrees, the diatomic hydrogen goes back and recombines, the monatomic hydrogen recombines the diatomic hydrogen. And when it does that, it gives up heat. So there's something that in the plasma physics literature they call the reactive thermal conductivity. You get a conductivity, an effective conductivity, because the monatomic gases up here, by the time they get down here, have recombined and created energy of recombination, released their energy of dissociation. This is the dissociation energy that they picked up here. They release that energy and they deposit it in the workpiece. So you can actually get fairly dramatic increases. The hottest, well, people used to weld with atomic hydrogen torches. They used 100% hydrogen. The problem is they're welding steel, and then we get hydrogen cracking in the steels, which wasn't such a good thing. I've only seen one atomic hydrogen torch in my life, and we found it in the dregs of the welding laboratory back in some little cabinet once. And I looked at this thing. They're weird looking things. They're kind of two long steel rods, and you put carbon electrodes on the end, and you have some tubes coming in. You blow hydrogen in there, and just kind of create an arc with some hydrogen gas, and just a very hot arc. Okay, because it has both low thermal mass, which gives a big thermal conductivity, it also has the heat recombination. And in fact, somewhere here, I don't think I have a copy of it. If you look at the thermal conductivity of a diatomic gas, as a function of temperature, you'll see a peak, okay, where it has very high thermal conductivity because of this reactive thermal conductivity, okay? So anyway, that's maybe a minor point. The last point is we also typically weld with carbon dioxide. And carbon dioxide has a high molecular weight, but it does give you an increase because it breaks down into CO plus oxygen, and you get the reactive thermal conductivity. So CO2 welding, which we tend not to use for high-strength steels because it tends to oxidize some of the alloying elements of the weld metal. We tend to use argon with 2% oxygen and stuff as a shielding gas, or argon helium mixtures, sometimes with a little bit of CO2, like 2%. Anyway, there is an improvement with CO2 depending on how much CO2 you have. Okay, so heat transfer in gases changes on these principles. Yeah.
So the argon is used predominantly because of its low cost?
No, not low cost, non-oxidizing and cost. So it's the two of those, okay? CO2 is the cheapest, by far, okay? But 100% CO2, you can use it to weld a bridge, low-strength steel, because you don't care if you oxidize out 1/3 of your alloying elements out of the steel, and how much you oxidize out depends exactly on how fast that guy's welding. And so you don't get the exact same uniformity of deposits. But if I'm welding 100 KSI submarine steel, I better use something where I have predictable properties, so the argon doesn't have this oxidizing of the alloying elements out of the weld pool, which is a variable thing depending on current, voltage, travel speed, and other stuff. So the other thing is, we'll talk about it later, the metal transfer is very nice in argon-oxygen mixtures. It's not so good in CO2, and people have tried a lot of things on power supplies to try to improve the way the drops go across the arc, okay? You'll get a beautiful looking weld bead if you got everything set up with argon. So it's a little more expensive, probably 3 times the cost of CO2, but a very high quality weld, okay? But still a reasonable cost. I mean, your gas cost is 1% of your cost. I mean, most of your cost is your materials and your labor cost. Yeah.
Is there any difference between shielding gas for welding and a forming gas that you use in like a brazing application?
Forming gas is basically just a mixture of nitrogen and hydrogen. In fact, forming gas originally was cracked ammonia. If you remember, ammonia is NH4. So ammonia gas is nitrogen and hydrogen, and it's a liquid, or can be a liquid, with slight pressure at room temperature. So you can put it in compressed tanks at 100 psi or something, and you can have liquid ammonia. You also use ammonia as a refrigerant in many cases because it's relatively inexpensive. Under certain conditions, it can explode. So I had the world's largest ice cream plant in Lamar's, Iowa. They did $40 million worth of damage when they had an ammonia leak, and they had several inches of ammonia on the floor. And it got to, we don't know exactly where the ignition source was, because this place was about half the size of a football field. This was the compressor room for compressing the ammonia. And they had like 20 compressors about the size of a good size, or half the size of a semi-trailer, okay? And one of them let go, it created the ignition for all this ammonia. And they blew the roof off the building and stuff. No one got hurt, but kind of shut down the ice cream production for a while. Lamar's is an interesting place. You walk into a drugstore or the grocery store or a service station, and they have free ice cream. They just have a freezer there, and you pick up some Wells Blue Bunny, and it's free. Because everybody in town works for Wells Blue Bunny. Okay, but anyway, but it is the world's largest ice cream plant. In any case, NH4 is easy to transport, and if you crack it, you can end up forming nitrogen and hydrogen in a mixtures, and now you have something that's reducing, so you'd like to do heat treating. Nitrogen is relatively inert for heat treating of steels and aluminum and things like that. But the hydrogen is nice because it's reducing, it keeps things from oxidizing. And forming gas that Ryan's asking about is basically, there are all kinds of ratios of nitrogen to hydrogen that you can buy forming gas in these different ratios. They call it forming gas, I don't know why they call it forming gas, but usually it kind of comes back to the fact that people used to use ammonia as a heat treating gas. So anyway, there are different heat intensities from different gases, and it may not seem like much, but getting an extra 40% or 60% heat transfer is a huge difference. Because in a gas tungsten arc weld, if you're welding on that pipe, it turns out those lower heat intensity, or not lower heat intensity, but those lower amperage arcs are only in terms of melting efficiency. In terms of efficiency of heat getting into the workpiece, they're about 50% efficient. We talked about that before. The other heat goes off in hot gases and other things. But in terms of melting efficiency, heat to melt the fused area, they're only about 20% efficient in an argon arc, let's say. And the other 30% of the heat, 50% of the heat got into the workpiece, but only about 20% of the total of 50, which is 40% of the total, goes into melting the weld pool, and the rest of it goes into creating the heat affected zone, heating up the solids surrounding the weld pool. So 50% gets in, but it's less than 50% efficient again at melting metal. So if I get an extra 40% heat in, I actually can effectively double the amount of metal that melted, because all that extra heat is much more efficient, because everything, the heat affected zone is already preheated, if you will, from the first 80%, right? That extra 60%, a lot of that extra 60% goes into the efficiency of melting, increasing the efficiency of melting. So far, are people following what I'm trying to say there? Okay, at least I get some positive notes. You don't all have to follow everything. You can talk about it afterwards. I'm sure you spend your afternoons discussing whatever goes on this class. Anyway, so a little bit of increase in melting efficiency can have a big effect on melting. But there are other things, and I guess I'll tell a story now. This probably occurred about 1978 when I was still in my late 20s. I was a young professor, and we had a Boston Navy Yard over here. And I needed the money, okay? And when I came back here from working in industry, I took a 30% salary cut. I had, 1978, I had 4 children under the age of 5, okay? And we were living in an apartment probably over in Watertown, or I don't remember when, about 78, maybe we were living in Beaumont then. Anyway, I got a call one afternoon. They had a problem welding the chrome moly steel tubes in the boiler to the carbon steel tubes. The chrome moly steel is a high temperature steel. I think we talked about that a few days ago. And the carbon steel is good at low temperatures. This was the high temperature steel that went into the boiler. These were the pipes that were running into them, okay? And you had to make a weld between them. And these were not big, these were like 3/4 inch tubes. And this destroyer that was being repaired over here, they had been trying to make these welds without hydrogen cracks for 6 weeks, and they had not been able to qualify the procedure. Now this was not exactly a new procedure. It had been around for years. I mean, people have been using these steels in boilers for, half a century at that point. But whatever happened, they were doing gas tungsten arc welding, using 100% argon. The only moisture that would be around would be a little bit of residual moisture in the air that gets in there, but a little bit of hydrogen. The chrome moly steel was giving them fits, and it turns out they had to use, according to the NAVC spec, an EB insert. And EB stands for electric boat. And the EB insert looks like this in cross section. Of course, this is the center line here. Okay, but an EB insert, they basically take a piece of wire and they mill 2 grooves on it to make this kind of funny cross section, and they make a little ring out of it, and they put it on the inside of the pipe. There's another one down here, you know, at the other end, right? With the other, and when you do that, it's an expensive way to do things, but you get a very good, if you melt this in properly, you get a very good bead on the inside of your pipe. Not a lot of drop through and stuff. So you want to melt that. Now, this was a thick enough wall pipe that they had a joint preparation that looked like this. Okay, I guess I didn't have to draw this many times. And here's the little EV insert. And the guys were gas tungsten arc welding this with no filler metal, and they had to prove that they could do it without a crack. Now, they hadn't been able to do it in six weeks. They had people come up from the Philadelphia Navy Yard to show them how to do it. They hadn't been able to do it. Whatever happened here in Boston, they couldn't do it. And the Navy required that you use an Inconel, I remember, insert. And what they found is if they used a stainless steel insert on this thing, they could make crack-free welds, but not with the Inconel insert. And so what they really wanted when they called me up was they wanted some consultant to come over and tell NAFC that it's okay to use stainless steel rather than Inconel, and we can get this destroyer out on time. And I didn't know. Shoot, I wasn't even 30 years old. I didn't have any white hair. Okay, couldn't hire me as a consultant. I mean, without white hair. But anyway, they asked me to come over. I stayed. Used to take the bus in at that time, and I stayed late. Went to the library, looked in the welding journal, and found out the reason you had to use Inconel rather than stainless steel is because if you didn't use Inconel, 10 year later you could get a high temperature cracking, creep cracking and stuff. So there was a good reason why NAFC had their spec. That's not always true, by the way, but in this case there was a good reason. Okay, and so I go over to the Boston Navy Yard the next morning, and there's like 10 people. This is one of my first consulting jobs, and they're all standing around. And I explained to them, I had a copy of the paper or whatever, explained why, no, you have to use Inconel. And they said, well, what are we going to do? And they explained to me their problems and their joint geometry. And I said, well, actually to myself, I was saying, I don't know. I just want to get out of there because clearly this was way beyond anything that I knew about. So the only thing I could think of, in hydrogen cracking, we actually often draw it as a Venn diagram. Hopefully you guys have already learned in your math courses what a Venn diagram is. A Venn diagram is you draw a bunch of circles to see where the intersections are, right? Well, we often, for stress corrosion cracking or hydrogen cracking, draw a Venn diagram. You have to have a material that's susceptible. You have to have a stress. And in the case of hydrogen cracking, you have to have hydrogen. In the case of stress corrosion cracking, you have to have a corrosive environment. And when you get all three of them in a big enough quantity, that's when you get cracking. And so if you can reduce any one of these three, you can make this intersection in the middle smaller and therefore less propensity to cracking. You increase the stress, you increase the hydrogen, greater propensity of cracking. So whenever you're trying to solve a problem, you know that if you can reduce any one of those threes. Well, I had already found out I couldn't do anything to material. Okay, that's what I researched the night before. Hydrogen, well, they are using gas tungsten arc welding. It was a residual hydrogen. There's always like 1 or 2 ppm hydrogen in the atmosphere, even when you're using pure argon and stuff, because there's moisture on the steel, even if you preheat it. It doesn't matter. There's always hydrogens everywhere, okay? And so you always get a little bit. So there I had, the only thing I could work with was stress. And this is actually how I'm thinking about this problem. And actually, I'm hoping to head for the door, okay, and leave them with their problem because I didn't know the answer. I said, well, you can change your joint prep, and their joint prep had been this, right? I said, why don't you change your joint prep and make it a J groove prep like this? Because now when you put your little EVA insert and melt this, there'll be some flexibility. It's not as stiff as up here, right? Here, this thing's super stiff. This is not anywhere near as stiff. So hopefully that relieves my residual stresses. And I said, I drew that for him and said, so try that, I'll see you. Started heading for the door. The guy said, wait, we'll do it. Hang around. And so we went out, and the guy goes over and he machines the two things on the lathe, and we're standing there, and the foreman, shop foreman, the whole time he says, "This is not going to work." Okay? He would just say this about every 2 minutes. "This is not going to work. This is not going to work." So they machine it, they weld it, they have a welder weld it. Then you have to wrap it in a blanket because this chrome moly steel has to cool very slowly, or you'll get a very high hardness, which increases the hydrogen cracking propensity. And so you wrap it, you thermally insulate it at that time it was probably an asbestos blanket. Anyway, and you wait 30 minutes. And the whole time, you know, every 2 minutes, "This is not going to work, this is not going to work." So we wait 30 minutes, take the blanket off. Now we have to do a dye penetrant test. You know what a dye penetrant test is? So dye penetrant, they first clean it, that's just spraying some solvent on. Then they spray the red penetrant on, this liquid, and you have to wait 15 minutes more while this thing penetrates. This is not going to work, this is not going to work. And I just wanted to head for that door, right? I'm this little punk kid, about your age. Okay. And so then the foreman takes the white developer. You spray this white stuff on to bring the red out, and he sprays it on, he's turning it, no crack. And I walked out a hero rather than a sucker. Sent him my bill for a couple $100. Anyway, and they got their ship out on time. Okay, so I only tell you the story because it was a successful outcome. Probably wouldn't tell you the story if it was an unsuccessful outcome. And I really didn't know what I was doing other than going back to the fundamentals, and knew that I couldn't do anything with this. I didn't even know how to get that any lower. They were doing a good job in terms of their general procedure. The only thing I knew to play with was stress, and the only thing I could think of was just reduce the stiffness of the joint.
Did anyone feedback to you why the other yards didn't have this problem?
No, they had flown in people and had them there for a week. From, I know the Philadelphia Navy Yard, I think NAFC had been up. You know, they may have talked to David Taylor, they may have had some David Taylor people up, and you know they didn't have the problem in other yards. It could have been humidity in the air in Boston, although there's humidity in most shipyards. Okay, you know that 80% of the time in an electric boat they're welding beyond the NAFC limit of humidity, right? Okay, there are specs in the welding spec at NAFC about how much humidity you can be welding in because of hydrogen. And 80% of the time they exceed the spec. But what are you going to do? Shut down the shipyard 80% of the days? You know, wait for a good wind? You know, that's just the way it is. So anyway, there are actually a number of principles there in terms of thinking about a problem and just, you know, I didn't know the answer. But that's what this course is supposed to be about. You know, you don't know the answer, you just kind of work your way through it.
With that up there, you just reduce the stress concentration factor, or?
No, the whole thing was more, well, it's more flexible, okay? You're actually, you could be right in the fact that here, if the actual weld bead you end up with may have had a sharper notch here than this one, so it could have been both a lower stress concentration and a more compliant joint, less stiffness, and therefore less residual stress when you got thin wings. I mean, I made them make these things like 3/8 of an inch, so this whole thing was like 3/4 of an inch. This is a little piece of sheet steel when we were actually welding, right? So they only had to get the root pass in with Inconel, because the rest of it, you'd fill it up with stainless steel, and the stainless steel wasn't a problem. But on the inside here with the root pass, you had to, I may have some of these things backward in terms of Inconel and stainless, but I remember all we had to do was solve the root problem. And so they changed their joint prep, but it also tells you that small little changes in weld joint procedure could make a big difference. But you don't just change them randomly. You got to have, when you're trying to work your way through, you work your way through based on the fundamentals. And that actually is one of the strengths of the MIT education. We don't teach a lot of practical things. In fact, to tell you another story, when I was a student here, one of my undergraduate scholarships came from the American Foundryman Society. And Harvey Cohen, one of my classmates, and I both had one of these scholarships for the American Foundryman Society. It was only a few $100 a year, but they were trying to hire, you know, they were trying to support students that they maybe later would hire into the foundry industry somewhere. And so they had, I went to it twice, once my junior year and once my senior year. the Drake Hotel, which is a nice hotel, used to be a nice hotel, right across from the Playboy Club in Chicago. I don't know why they were sending us under 21 people over there, but anyway, they'd have a convention. They would fly you out and let you go to the convention, and they told the story, and the story is actually the same as the story I heard about the old sea captain, the new commander, who he'd just taken over his new assignment, and people thought it was very nice that at the beginning of each day he would sit at his desk and he would just have a silent moment and to begin the day. And then it turns out about a week later someone was there and they were looking over and he actually pulled out the middle drawer and it said, starboard is right, port is left. Okay? And so they actually told the same story at the American Foundrymen's Society, only it was the foundrymen who took over management of this foundry shop, and they were looking over his shoulder and it said, cope is on the top, drag is on the bottom. The two halves of the mold are called the cope and the drag. The drag is on the bottom and the cope is on the top. And so he had this little reminder there each day of which one was which. And they tell this story, and Harvey and I look at each other, and we didn't know what a cope and a drag were. And I've been working in the MIT foundry for 2 years. Okay. And I've been working with copes and drags, but they never told us what they were, the name of them. So there's not a lot of that type of practicality in the MIT education, but there is a lot of the fundamentals. And if you go back to the fundamentals, you can actually learn and work your way up. So I actually am a proponent of the MIT way. Although when you're going through it, it's hard to be a proponent of it. Anyway, so let's talk about how the heat is we talked about the heat transfer, but it turns out that we sometimes use electrode negative, which we use for gas tungsten arc welding, and that's called DC electrode negative, DCEN, or straight polarity. Okay, American Welding Society calls it DCEN. The rest of the world usually says it's straight polarity. Now, the American Welding Society has some very precise definitions because there was a guy named Halleck Campbell who was a Harvard grad who used to write their definitions for them. Okay, and Halleck was a real stickler. Okay. Anyway, if you have a tungsten electrode, it's up there. Right? We were talking about an electrode and an arc in the base material. If you have a tungsten electrode, it turns out, and the tungsten electrode is not going to be consumed, you tend to use straight polarity. This electrode is negative, which is the cathode. They call them cathode rays because the electrons come out of the cathode.
So this is an electron rather than pole flow.
Yeah, this is electron. This is a gas. So this is an arc. So it's electron flow. So electrons are coming out of the cathode. And I have something called cathode spots where the electrons come out. And this whole cathode emission there's 20 different theories involving quantum mechanics and other things to explain how electrons can get out of the metal. Remember I told you the electrons get in and they go down to the Fermi energy. Well, why does one want to come out of the Fermi energy to a higher energy state? I got to pull them out somehow. And if you go through the basic physics of how do you excite an electron from way down in this low energy state at the Fermi level in the metal to exciting it out into the gas phase, it's very complex. You have to try to use quantum mechanics and no one can agree on how it works even today. And they've been studying it since the 1920s. Okay? The reason they used to study it a lot is because vacuum tubes worked on this same principle. You have to have a cathode and an anode in the vacuum, and how do the electrons get out into that vacuum space from being bound in the metal? Okay? So anyway, the anode the electrons come out of the cathode and they hit the anode, and the electrons go into the anode, but they're coming out of the tungsten. Remember I said the electrons carry the current. It turns out if you measure the heat to the electrodes, you'll find about 1/3 of the heat goes into the tungsten from the arc, and 2/3 of the heat goes into the anode. We're talking about, well, these are typical types of numbers. About twice as much heat goes into the anode as into the electrode. I told you before that it might be 50% of your total heat goes into the anode. That might be 25% of the heat goes into this tungsten electrode and heats it up, and you have to keep it cool, usually because you shroud it with a little copper. You put in a little copper collet, copper carries the heat away. But that tungsten gets hot. It's glowing red hot at about 2,000 degrees centigrade while you're welding. But tungsten melts at 3,300 degrees centigrade. But the anode gets 2/3 of the heat, and the tungsten only gets 1/3 of the heat. And it turns out Professor Savage at RPI had a student a number of years ago who basically used infrared thermography, and actually this is supposed to be a little picture of temperature up here. You can hardly see it, it's in red and stated. But temperature, he actually found the hottest part of the tungsten electrode was not right at the tip, but it was just back a little bit, because the electrons coming out are taking the heat of the work function heat, which is the energy from the Fermi energy up. They actually have to cool off that tip slightly. So the maximum heat here was actually back further because the electrons at the tip are actually cooling the tip of that electrode. And they carry that extra heat back down here to the anode. So the tip is cooled by evaporation, and I remember Professor Savage telling me, he's passed away years ago now, but he told me that all of a sudden he understood why when you look on x-rays of gas tungsten arc welding, for example, a lot of times on aluminum, you would see not little circular tungsten inclusions because the tungsten tip melted and ended up creating a ball, but he would see little rectangles of tungsten. And it was because the tungsten electrode actually melts off if you get it too hot, put too much current through it, it'll melt off back here and you'll get this little rectangle when you start taking images of it. You actually break off tips, if you will, or melt off tips. And I've talked to other people over the years, and they say, oh yeah, tungsten inclusions often are not little spherical balls from melting, or they don't know it's from melting, but they say, yeah, they have edges on them in corners. And that's because the tip actually is hottest right up here. Now, you can now see if you get most of the heat to the workpiece, and in gas tungsten arc welding, let's say we're trying to make one of these pipe welds, we want to put the heat not into the electrode, but into the base plate, because that's what I'm trying to melt. So I tend to use straight polarity. There's some other reasons I use straight polarity, which we'll get into later. If I'm doing gas metal arc welding, where I have a steel electrode that's going to have drops melting off, I actually change to electrode positive, which we call reverse polarity rather than straight polarity. And the anode becomes the wire, and the cathode is the workpiece. So for iron, aluminum, nickel, we typically will have this as the anode. And why is that? Because that's what I'm trying to melt. I've got a groove that I'm going to try to fill up with big blobs of weld metal, okay, weld beads. And I'm going to try to improve the efficiency of my process by putting my 2/3 of the heat into the wire, which is what I want to melt. And I don't really need to melt much of the base plate. I just need to fuse it so that I get good fusion inside that little V groove. Okay? So one way to think about these processes and what type of polarity is the anode is, or the material you want to melt in gas tungsten arc welding is the base plate, whereas the material you want to melt in gas tungsten arc welding, or in gas metal arc welding, is the electrode itself. So, any questions? If not, we can call that a day. And I got to talk to you about schedule.